Thanks for the invitation and also for the introduction. So this work is based on joint work with Lam and Rongchen. So our paper was already on the archive. So we will talk about this 5,4D field. So this 5,4D model is the simplest non-trivial Euclidean quantum field. And so this model, in fact, if we is formally defined in the following way. So we can see that formally this part is the product measure of the Lebesgue measure, and but we are in the infinite dimensional space, and this part is the Hamiltonian part. And formally we have this. If we just ignore this fourth power term, so this part is just the Gaussian free field part. For this Gaussian free field part, but we want to have some nonlinear interaction. So we have this fourth power term. And formally, it looks like this measure can be viewed as a Gaussian free field with a density, with an absolute continuous density here. But when even in d equal to 2, this Gaussian free field is not taking values in function space, but taking values in distribution space. So this phi is not function valued, but distribution valued. So how to make sense of this fourth power term? This should be a problem. So so in two-dimensional case, we need to do this weak renormalization to give a meaning to this fourth power term. And in three-dimensional case, in fact, we need to do more. This weak renormalization, because Gaussian free field is more rough, and we need to do more. And in two-dimensional case, this measure is absolutely continuous with respect to this Gaussian free field in finite volume case. But in three-dimensional case, this measure is not absolutely continuous with respect to this Gaussian free field. So this is a formal definition. So we need to do more renormalizations to give a meaning to this measure. And in fact, in this during 60s to 90s, a lot of mathematical physicists like Lelson, Glim, Jaffe, Simon, Feldman, Spencer, and Bridges, they developed this so-called constructed quantum field theory, and which can be used to construct this 543 measure. And also recent work about this 5,4D model is by this Eisman, Domina, Kopin, and they can prove that from this lattice approximation, no matter how you do this renormalization, but in this high temperature regime, the limit measure, the marginal distribution of the limit measure is Gaussian. So this is for this constructive quantum field theory for this model. And this model is also related to this statistical physics related to this phase transition. So this formula, this part is a kinetic energy part of this Hamiltonian, and this part is the potential part of this Hamiltonian. And then when this m is negative, so this potential energy will have two minimum. So formally in the infinite volume limit, so this 5,4D model is not unique. And when this m is become large, become positive, so there exists there is only one unique minimum for this potential. So when this m changes from this negative to this positive, so this is like from this easy model changes from low temperature regime to this high temperature regime. So and there exists a critical temperature, and at this critical temperature, there is a universality conjecture. It is believed that at this critical temperature, the behavior of this 5,4 model is the same as this Ising model. And also recent work is by Goldschmidt and Dagnier, and they can prove this under this high temperature regime. They can prove the log Sobolev inequalities for this 542 and 543 model. And also this model is also related to the following nonlinear Schrodinger equation. So formally, this measure, it is an invariant measure for this nonlinear Schrodinger equation. So we can see this nonlinear Schrodinger equation is written in this way. And since this 80s to 90s, people are interested in this equation with low regular initial data. And for this is initiated by this Leibniz and Rose and Spiel, and realized by this Begin for this 542 model. And he can prove that he can first prove the local approximateness of this model when the initial data is in the C minor space. And then by using this, he can prove this in Meyers and 542 Meyers and invite Meyer for this equation. And then by using this Begin's argument, and he can obtain the global approximateness of this equation from almost every starting point. And recently, this model, this result has been extended by Deng, Lambda, and Yue to this P52 model, which means that it changes this polynomial, this 5 to the power 4 term by this general polynomial term. So this is this 54D model related to this, and this 54D model also related to this stochastic PDE. So this is and before this PDE is a parabolic, is a dispersive PDE, but this is also related to this stochastic parabolic PDE. So we need to, so we still have this derivative over this Hamiltonian part, but it's a parabolic PDE part, and we also need to add in this space-time white noise here. So we have this is a stochastic PDE. So this size space-time white noise. So this is so-called the stochastic quantization of this Euclidean quantum field proposed first by this Paris and Wu, which is trying to get in this field as the stationary distributions of this process. And in two-dimensional case, this has been done by this Giordano and Meter, and also Avera and Rockner by using this Dirichlet form approach, and also by Daprato and Debush, and they decompose this equation into this linear equation with this noise part and a nonlinear equation. But all these tricks breaks down in three-dimensional case, because in three-dimensional case this is more rough. Because here, to understand this equation, we need to do renormalizations. Here, because in this noise is the regularity of the noise is related to this dimension here. So here, this psi is formally living in such kind of space, in parabolic space. So in this minus d plus 2 over 2 minus regularity space. So in two-dimensional case, we can see that this psi is already in C minus 2 minus regularity space. So by Schauder estimate, because now we have this parabolic operator, so by Schauder estimate, we can get 2 regularity. So this in two-dimensional case, this phi is already a distribution value. So it's in C minus regularity space. So how to give a meaning to this cubic term? This should be a problem. So here we need to do renormalization. So here in two-dimensional case, this weak renormalization is enough to give a meaning to this one. So this minus infinity is formally, so we need to approximate this equation with modifier for the noise part and give a meaning to this product terms by using weak product, and finally to give a meaning to this equation. And in three-dimensional case, this is a more, because the noise is more rough, and this tricks breaks down. So the breakthrough work is by this highest regular structures, and also this paracontrolled calculus by Gubinelli, Keller, and Perkovsky. By using these two methods, we can give a meaning local approximateness of these equations. And also recently, because of these works, we can understand more about this dynamic 5-4 model. And global approximateness in finite volume case has been obtained by Morant and Weber. And also for the infinite volume case has been obtained by Gubinelli and Martina. Also, because now we understand more about these equations, we also want to use these equations to understand more about this 543 field. And there are also ways from the dynamics for this 54D field. There are some works. First, it started by this Avera and Kusuka, and also by Gubinelli and Martina. And they can use this PDE constructions finally to give new constructions for this 543 field. And also recently joined with Hao and Scott and Rongchan, and we can also obtain this larger limit of this, use this stochastic quantization to study this larger limit of this O(n) linear sigma model, which means that we consider this vector value phi 4 and study the larger limit of this model. So this is recent work, and also there are also this variational approach proposed by this Brashkov and Gubinelli, and also this renormalization group approach and the flow equation approach by this Kupiana and Duh. And recently, by using this approach, they can construct this fractional phi 4 3 model to cover all the subcritical regime. This is recently work by this Duke, Gubinana, and Ali. So this is the progress for this by using this stochastic quantization for this phi 4 3 model. And now today I want to talk about to use this phi 4D field to try to describe this Bose gas as this criticality. Especially we want to understand this Bose-Einstein condensation forms at this phase transition. So this Bose-Einstein condensation actually means is in this 1995, and it has been observed in the experiments, which means this many bosons will occupy this ground state at a very low temperature. And so this is a picture for this Bose-Einstein condensation. So from this picture we can see that when this temperature becomes lower and lower, and more these bosons will occupy this ground state here. So this will lead to a lot of macroscopic quantum effects like this superfluidity, a lot of things. So in fact, this Bose-Einstein condensation has been predicted by Bose and Einstein almost 100 years ago. And they predict this Bose and Einstein condensation for this long-interacting Bose gas. So this N0 just means the number of the particles, in the ground state. And this N means the number of the total particles. So from here we can see that there exists a critical temperature. So when this T is bigger than this critical temperature, there is no such kind of, this N0 is not comparable with this N. But when this T is smaller than this critical temperature, this N0 is comparable with this N. So there exists this phase transition, there is a critical temperature here. During that time, 100 years ago, they only predict such kind of condensation, but they cannot verify it by experiment, because at that time they cannot make this Bose gas in such a low temperature. Only until this 1995, and people they can really make this low temperature in reality and view observed such phenomena, this Bose-Einstein condensation in experiment. But this Bose and Einstein, they predict such kind of phenomena for this long-interacting Bose gas. So in mathematics, then, it is a major challenge to how to understand this Bose-Einstein condensation for this Bose gas with interaction. So this is a main problem here. And now, what we first we try to understand this many-body quantum problem mathematically. So first we try to understand it. So because we are working on this Bose gas case. So we will consider this. We are working on this Fock space. So we have this on each graded vector space. We have this symmetric subspace of the tensor product of the L2 space. And now for this Fock space, we don't need to fix the number of these particles. And for this, under each this graded space, we have defined such kind of Hamiltonian. So this Hamiltonian, so this part is like the kinetic energy part. So which means the Bose gas with some non-interacting case. And we're also adding some interactions between different particles. But here we just consider the simplest case. we consider these particles have only have two interaction, only between the two bodies. This is the simplest interaction here. And we consider this lambda is a semi-classical parameter. We're adding a parameter here. And this is formally our Hamiltonian written in the following way. And now we also define the Gibbs state here. So this Gibbs state is defined, looks like is similar like this quantum version of our Gibbs Meyer, defined like this phi 4 Meyer. But we just put this Hamiltonian also in the exponential part. And now we also take this the trace part of this z lambda is a partition function. So we take the trace of this operator here, because this is the operator, it's not the probability matter. We take the trace of it such that this Gibbs state is of trace 1, so it's a pure state.
Is it correct that there are two lambdas? There's one lambda in front of the H and one lambda inside the H?
Yeah, it's the same lambda. Yeah, it's the same lambda here. And now we also assume the Fourier transform of this V epsilon is positive, is non-negative. So which means that this operator is a lower bounded self-adjoint operator. So we can give a meaning to this Gibbs state. And for this one, for this Gibbs state, now first we can see if there is no this V epsilon part. So if there is interaction is just equal to 0. So this corresponding to this ideal Bose gas case, just corresponding to this Bose and Einstein's case. In this case, we can explicitly compute this one-body density matrix. So this just means with the marginal distributions of this quantum version of the marginal distributions of this Gibbs state. And now we can compute them explicitly. This is written in the following way. So we can use this one-body density matrix. Actually, we can compute explicitly this n part is just take the trace of this one-body density matrix, and this n0 is just taking this spectrum equal to 0, because this spectrum of this Laplacian is explicit. We can explicitly compute this n0 and this n, and then they can have such kind of formula. And we can also see that the behavior of this one-body density matrix after this scaling, so that it will convergence to this the correlations of this Gaussian free field. So we can see that for this non-interacting case, we can relate this one-body density matrix to this correlation of this Gaussian free field. But now we have this interaction case. So for interacting case, when this when this n is very large, so it is even this is a linear operator, but it's very difficult, even in this numerical sense, it is very difficult to study this Hamiltonian, the properties of this Hamiltonian, because of this interaction. So our aim is try to relate this many-body linear theory to a one-body nonlinear theory, try to use related to this Gibbs Meyer. So this is our aim. So this is the case for this many-body quantum problem. So first we want to see why this will be true formally. So we first use the so-called this second quantization to introduce this annihilation and creation operators to rewrite our Hamiltonians. So this annihilation operator means that we map this n particle state to this n minus 1 particle state. So we can see that, so we have this n particle state. And now we map just taking one of them, just taking values at this x point. And then we define it like this way, so we need to do symmetries of them. And the adjoint operator is a creation operator. So which means we map this n particle state into this n plus 1 particle state. So we were just adding this delta x here, but this is not delta, is not L2's function. function. So this is formal, but we can make it rigorous by test function to make it rigorously. And it will satisfy this canonic commute relations. So which means for this ax and ay it commute, and ax star and ay star it commute. But for this ax and ay star it does not commute. So there is this delta because it's operator, so it's not function, does not commute. But by using such kind of operators, we can rewrite our Hamiltonians in the following way. So we can see this is our Hamiltonians recoils in the as it is defined as before. And now by using such kind of operators, we can rewrite this Hamiltonian is written in the following way. So this is already looks very similar like the Hamiltonian of this Gibbs Meyer, like this phi4 if we just change this v epsilon to this delta function, delta x minus y. But now we have such kind of Hamiltonian, but this is operators and we also have this lambda here. So we can also do this and this ax and ay, this part is not commute. But we can still do this rescale this ax by this square root of this lambda. So we can see that we can have such kind, we can rewrite this Hamiltonian by this bx part. And we can see that when this lambda goes to 0, formally this bx and by star will becomes commute. And formally we can just change this bx and bx star by this psi x and the conjugate of this psi x. So we just change these operators by functions. And now we can see that this part, so this is just looks like this Gibbs Meyer already. So formally we can see that this is our limit Meyer, so we can get this Hartree phi4 Meyer as our limit Meyer here. So this is, so we can see that this is just the Gaussian free field part. And this is our nonlinear interaction. So we just changes this b star and bx here, changes to this phi x square, and changes this to this phi y square part. So this is formal why this will be true in this case. But this mathematically this will be challenges since because now all these things are operators because they do not commute. And the first work in this direction is by this Levin, Lamb, and Rogeri. And they can do it for this fix this epsilon, just take the epsilon equal to 1. And in one-dimensional case, and they finally they can prove this partition function and the density matrix will convergence to the partition function and the correlation function of the Hartree 541 model. This actually has, they use this variational approach to finally prove the result. In two-dimensional and three-dimensional case, also for this Hartree model, this has also been done by this also by this by them and also by this Follick and Lolledge and Schlein and Schrödinger, and they by the two groups, and they can also prove this such kind of result by using different methods. Still by this Levin, Lamb, and Rogeri, they use this variational approach, and this Follick, Lolledge, and Schlein and Schrödinger, they use this path integral approach. And they can also prove the similar result holds for the two-dimensional and three-dimensional case. But now, because now, as mentioned before, even for this Hartree Meyer, because this Gaussian free field is not taking values in this function space, but taking values in distribution space, value space. So for even this V epsilon is smooth, but we still need given meaning to this phi x square term, we need to do renormalization, and the phi y square term, we need to do renormalization. But now this weak renormalization is enough. So here they still need to minus the corresponding terms in this quantum many-body part. So need to minus this rho lambda term, which corresponding to this chemical potential part, and with corresponding to this renormalization constant. And then they can give them, and then they can prove that such model will finally convergence to this Hartree 542 and 543 model. So this is the result they can obtain. And
Okay, what exactly is the convert? I mean, is it the correlation functions of correlation?
Correlation function and also this partition function convergence. Yeah. And also later by this following knowledge and Schlein and Schrödinger, and they also let this epsilon and lambda goes to 0 simultaneously. And then this V epsilon will converge to this delta function. And then they can prove that the limit measure is complex valued 542 model. And here, for this 542 model, compared with this Hartree measure, they need to do, because when this V epsilon converges to this delta function, they need to do more renormalization for this different point x and y. Here, they need to add the suitable weak renormalizations such that this will finally converge to this 542 model. So this is a result by previous result. So our main result is try to extend their previous work to this three-dimensional case. We try to prove that this will finally converge to when this epsilon and lambda goes to 0 together and V epsilon goes to this delta. And this Hamiltonian, this quantum many-body will finally converge to this 543 model, the correlation function of the 543 model. So this is, we first recall our model. So this is interacting Bose gas. So this is, we still take this V epsilon, it's our nonlinear interaction here. And formulate when epsilon goes to 0, it will converge to this delta function. And for this part, we will also have this nonlinear interaction, and this is a kinetic energy part. And this theta we just is a chemical potential. And we want to choose this chemical potential part such that this corresponding to the renormalization terms, and such that this part will finally converge to this 543 model. So usually we will do this weak renormalizations to give a meaning, so that we will do formally weak renormalizations for this model. And we will also have, for the 543 model, we will also add this log divergence to do renormalizations. But this, when we do such kind of renormalizations, we will see that in the limit measure, we will have a new mass term. So this C1 and C2 terms will appear in our limit measure. But we can also put these two terms into this chemical potential part, and then the limit will not appear this C1 and the new mass term. So I will explain. So this is our main result. So we have this Gibbs state is defining, we can still define our Gibbs state. So this is a quantum version of a probability measure, and with such kind of interaction. And now we have our potential. We assume such kind of conditions for our potential. We assume it is a non-negative potential and in this L1 space. And we also assume this potential, the integral of it is equal to 1. So this will let this V will converge into this delta function. And we also assume a fully transform it will have such kind of decay. So this formula means we need a fully transform of this V will in this L1 space. So for this delta bigger than 0, this is enough. And we also assume such kind of conditions here for the derivative of this Fourier transform of this potential part, interaction part. So here we can see that this basal potential will actually satisfy our condition when this beta is bigger than 3, and for this basal potential. And now we're adding our chemical potential part. So this corresponding to this renormalization constant here. So the first part is corresponding to this weak product comes from this quantum part, is related to this weak product related to this ideal Bose gas case. So this is just this phi square, just the phi x square part. We need to do renormalization, weak renormalizations. Then we need to minus such kind of terms. And this part is for this renormalization according to this phi x square and phi y square. So this part is of order 1 over epsilon. And this is the renormalization of this log divergence. So we have such kind of renormalizations. And this G is a green function here. And now we assume that this epsilon and lambda goes to 0 together. And compared to this lambda, this epsilon goes to 0 slowly. And then we can prove that this density matrix of this Gibbs state, and this means like our correlation functions of a probability measure, like the marginal distribution of this Gibbs state. And after this rescaling, multiply this lambda to the power k, it will convergence to the correlation functions of this 543 measure. So this is our main result here. So for this.
Yes, this counter term, you could also use the same as the usual one.
Yeah.
It's the same, right?
Yeah, it's the same. Yeah, this is the same as the usual one. But the usual one, we will appear such kind of two counter terms, this C1 and C2 term. But if we don't want to see such kind of C1 and C2 in the limit measure, we can just put this C1 and C2 in this chemical, into this part. We just minus them, then we will not see this C1 and C2 in the limit. Yeah. And now our result, our proof is based on two steps. One step is based on this stochastic quantization method, as I mentioned before. So we use this stochastic quantization and paracontrolled calculus proposed by Gubinella and Imkera and Prokofsky. And we can prove that this Hartree 543 model actually will convergence to this 543 model. So the Hartree model is written in the following way. And then the second step is based on this variational approach. And we can use this variational approach from this quantum many-body, to this Hartree 543 model. So this Hartree measure is written in the following way. So this dot means that we have already do the weak product for this square term. This part we have do it already. And now we also need to add in this weak this renormalization term, this A epsilon part. This is corresponding to the renormalization over this X and Y term. And this log divergence is B epsilon part, and this is Gaussian free field part. But if you are familiar with this Hartree measure, so in the literature, usually people won't do this Hartree when for this some bad behavior kernels, then do this usual renormalization is to take this phi x and phi y. The usual weak renormalization is to take the renormalization of this phi x and phi y. So the usual renormalization is like this red term. So we can see that we take this renormalization over this phi x and phi y. We will just get our green function here. And then we can see that we have such kind of nonlocal terms here. But for this nonlocal terms, we can also prove that it will converge into this 543 measure. But with this, we will not see this new mass term, this C1, the C2 term. But when we do such, first we do such kind of this is a lateral of Hartree model, which converge into this 543 model. But we don't know how, if we consider this Hartree model, we don't know how to associate this model in this quantum many-body problem. Because in this quantum many-body problem, the only parameter we can adjust is this chemical potential part, which means we can only add in this constant part here in this Hartree 543 model. And this change will finally leading to this C1, the C2 terms here. So this is for this Hartree 543 model here. So for the now we finally have our two results. So first the result is that from this quantum part, so we can prove that when this lambda goes to 0 and the epsilon is bigger than this lambda here, and is low, and we can prove that from this quantum many-body, it will converge to this Hartree measure here, uniformly in this epsilon here. And then we can prove that this Hartree measure will finally converge to the correlation function will finally converge to this Hartree 543 model. And now I want to explain a little bit more how we use this stochastic quantization to prove this Hartree-Meyer 543 model to convergence to this 543 model. So we can write this. We can write the stochastic quantization of this Hartree 543 model as follows. So we can write it in this way. So this is a parabolic SPDE, and we have this nonlinear term. And we will have this nonlocal terms. Actually, we will have this convolution operator here. And we will also have such kind of renormalization terms. And this psi is the space-time white noise. And now here, because for this part, we still need to do this. When this epsilon goes to 0, we still need to do weak renormalization for this phi square and psi epsilon here. And here for this part, the usual weak renormalization is written in this red part here. Is written in the following way. So we have this convolution terms. So we just add it, then minus it, and have this new R operator here. So this R operator actually, so this operator is, we have two terms. One is from this A epsilon part. So this A epsilon part is actually of order 1 over epsilon. And this V epsilon, this part is also diverge is of order 1 over epsilon. But when we take the minus of them, they will cancel. This divergence will cancel. And we can prove that when we lose one regularity, and this R operator, we can have uniform in epsilon bound for this R operator. And also here, by losing more regularity, we can actually see that this R operator will converge to 0. So this formula means that this operator will finally converge to 0. It will not influence our limiting. It will not influence our limiting equation. But here, because now for d equal to 3 case, this psi is in this c minus 5 over 2 minus regularity. So formally, this solution itself is also in this minus 1/2 minus regularity space. So when we take this R operator, it will lose one regularity. So it will live in this minus 3 over 2 minus regularity. So formally, this R, after this R operator, this part looks like this cubic term. The regularity looks like this cubic term. So this formula will lead in new renormalizations here. So because now in this stochastic, to understand this equation in the stochastic quantization, we first need to use this Daprata and Debush trick, and to understand this equation of this z. This is for this linear equation part, and for this z part. And for this z part, we will see that this is the worst part in the equation, and we will need to substitute them into this equation again, and we will see such kind of terms. And for such kind of terms, formally this z is still in this minus 1/2 minus regularity, and then this r is in this minus 3 over 2 minus regularity. And this I operator, after this I operator, it lives in this 1/2 minus regularity. And this z itself is still in minus 1/2 minus regularity. So making a product of them, we need to do renormalization. And after renormalization, it will live in C minus space. So usually this renormalization is in this log divergence for this cubic term. Similar renormalization, it will lead into some log divergence. But because of this R operator, this special form, we can compute explicitly this two divergence, this two constant, and finally it will converge into finite constant C1 and C2. And this is why this R operator will finally lead into this new two mass term, this C1 and C2 in the limiting equation. So, and this is why for our limiting equation, we will have this two new mass term. So we will have our find the solution to this dynamic 5-4-3 model, and we can prove that if the initial value convergence in this C minus 1/2 minus regularized space, then the solution itself will convergence to this Hartree model, will convergence to this dynamic 5-4 model with this new master. So this is only the convergence of the dynamics, and we still need the convergence of the Meyers. So here we still need to do more, and we let this psi epsilon be the stationary solutions to this Hartree dynamic 5-4 model. And then we can see that we can obtain such kind of uniform moment bound for this by using this SPD argument. And we can obtain such kind of uniform moment bound for this the solutions to the Hartree dynamic Hartree 5-4 model. So this is uniform over this epsilon. So and after we obtain such kind of result, we can obtain this implies the tightness of this Hartree Meyer. And by using this tightness of this Hartree Meyer, and we can let this Hartree Meyer as our initial condition here. And then this tight limit should be the initial value of this dynamic 5-4-3 model. So because this Hartree Meyer is an invariant Meyer for this dynamic Hartree model, so this means that the Hartree model, this is starting from this Hartree Meyer, so it is stationary solutions for this Hartree dynamic Hartree model. So then this means that when we're taking the limiting, so the limiting equation, the solution to the limiting equation is also the stationary solutions to this dynamic 5-4-3 model. So which means that because in the finite volume case, for the dynamic 5-4-3 model, the invariant Meyer is unique, which means that this limit Meyer should be an invariant Meyer for this one. It's a unique invariant Meyer for this one. So which means this Hartree Meyer will finally converge to this 5-4-3 model. So this is the way we use this SPD argument to prove the convergence of this Hartree 5-4-3 model to this 5-4-3 model with this new mass term. And here, because we also have this uniform moment condition of this piece moment condition here, and then this implies this convergence of the correlation function here. So this is how we obtain the convergence of this Hartree Meyer. So to obtain such kind of moment bound, so here we need to do this decompositions. And usually for this 5-4-3 model, people do such kind of uniform moment bound. They obtain such kind of result by using this maximum principle and or this LP energy estimate. But now for this Hartree Meyer, because of this nonlinearity, this is a nonlocal nonlinearity, we cannot have, we only have this dissipation in this L2 space. And for this Hartree equation, and here we do this decomposition. So we decompose the equation into this low frequencies part and high frequencies part. And for this low frequencies part, we use this L2 energy estimator. And for this higher frequencies part, we use this shorter estimate. And then by using this decompositions, and then we can obtain this coming down from infinity result. Formula means that our bound does not depend on the initial value. And this means that our right hand side formula, because this is usually this SPD argument, we will see the right hand side will depend on the initial value. And now we have this coming down from infinity result, which means the right hand side will not depend on the initial value. So we can obtain such kind of uniform bound and do not depend on initial value, which finally implies our final convergence of this Hartree model to this 5-4-3 model. So this is how we do this the first step. The second step is for this by using this variational approach. So this is similar like this previous work by this Levin, Lam, and Rogeri, but we need to do a quantitative version of it. So we use this Gibbs variation quantitative version of them. So this is, we first have this Gibbs variational principle here. So use this Gibbs variational principle. So the classic Gibbs variational principle is for these measures. So this means this measure will minimize this part. So we will see that this is a relative entropy part. So this part is always positive, and this part is the interaction part for this Hartree measure. So this Hartree measure is, we will have such kind of a Gibbs variational principle. And for this quantum version, we also have such kind of Gibbs variational principle. And by using such kind of Gibbs variational principle, we can prove that the free energy, we can first prove this free energy of this quantum part will close to the free energy of this Gibbs of this Hartree measure. So this is based on to establish this lower bound of them and upper bound of them, and for this one there is already this quantum definite theorem which works for this finite dimensional case. So which means that if this L2 space is do this finite projections, and then we can do some galaxy approximations, and then we will see that the corresponding this matrix density will finally convergence to this corresponding definite measure formulated, and it is close to this Gibbs measure and the correlation function of them. And also to obtain this low upper bound, we can choose, because this is like informal, we can just choose a special Gibbs state and to obtain this upper bound. And to obtain this lower bound, we still need to, we will use this Brownian Lieb type inequality to control such kind of relative entropy part by using this relative entropy of associated measure part. And also because this quantum definite theorem is only works for this finite dimensional space case, it only works for this low momentum part. So we still need to estimate this high momentum part. So for high momentum part, I can use some correlation inequalities for this high momentum. So this idea before this correlation inequality is that in this high momentum case, it looks like these particles do not interact. So they can have such kind of correlation inequalities, and then they can control this high momentum part, and finally they can establish such kind of result. And so by combining this variation approach, this quantum part of result, and also this convergence of this Hartree measure to 543 measure, and then finally we can obtain our final result. So this is our proof part. So this is the further outlook of our work. So for this Bose-Einstein condensation, they can compute explicitly for this N0 part. It's like this over this N is can be computed explicitly like this way. So this lambda is like the inverse of this temperature. And so they when this chemical potential changes, so this is when this chemical potential is have a looks like this lambda to the power 1/2. So this is means that there should be Bose-Einstein condensation will happen. So in this case, this N0 is comparable with this N part. And when this new N0 is zeta 0 is goes to this lambda over 1/2 minus 1. And this is like this, there is no Bose-Einstein condensation, means this non-condensed phase case. So how about for this interacting Bose gas case? This is not clear until now. And so in our case, if we just ignore all these renormalization counterterms, we just choose this zeta 0 is equal to 1, and this is just in between this case. So this will finally convergence to this 503 model. And now we already have this quantum version part. When this lambda goes to 0, the density matrix will converge to the correlation function of this 503 model. So whether we can still use this, because for this 543 model, there are a lot of results to study such kind of long-range correlation, or like this symmetry breaking, or like if we consider this vector value, the 543 model, like this Owen linear sigma model, and which also corresponding to this metabolic problem with n speeds. And for this case, we can also have such kind of 1 over expansion. So whether such kind of a result can help us to understand some interesting properties for this metabolic problem. This is this is still unknown. And that's all. Thank you.